सर पानी डाल, पानी दे दीजिए। Okay, good afternoon students. This is Abhinav Jha. I am BTech NIT Nagpur and I am from Delhi. So today I'll be taking up strength of materials topic. And this is the most important topic in civil engineering and mechanical engineering, as you would know. So I'll be basically discussing all the basic things which is required in this topic, what is the benefit of this topic, and how to study this topic. So these are the three main things which I'll be discussing today, and we'll be taking up this first chapter, that is the properties of material and axial strength, which is required in each and every interview of PSUs, ESC and whatever you call it. So today I'll be taking up this topic, properties of material and axial strength. Before that, let's try to know a bit about what is strength of materials. Like in all our general life, we make buildings, we design structures, railways, aeroplanes, whatever we call it. So we use steel, we use any materials, we use different kinds of material. That can be tensile material, brittle material, whatever you call it. And then we have to understand what is the strength of that particular thing. To understand the strength, we have to do plenty of analysis. There may be some force analysis, stress analysis, and internal material strength analysis as well. So in order to calculate all these strengths, we have to do design. For that design, we need to know strength of the system as well as the loading which is coming on the system. And to make a proper system which can sustain that load, it should be in proper orientation as well as it should have proper amount of strength. Okay, now this topic is most asked topic in civil engineering and mechanical engineering in GATE as well as ESC. This is the most weighted subject in civil engineering along with geotech, and in mechanical engineering it takes a lot of weightage. Okay, but the most important thing which I'll tell you from my side is that this topic is the most asked topic in any interview you go. Wherever you go in any interviews for PSUs after scoring a good rank in GATE or after clearing your ES prelims and mains, if you go there, they will just ask you simple thing, do you know song? And then you have to say yes. If you don't know also, you have to say yes, because they need the answer from this topic. And this is the most important topic in all engineering, if I have to say. Okay, so mostly in GATE civil engineering, it has a weightage about 8 to 10 marks. And it is not a very tough subject, I would say, but very conceptual. If you understand the concepts, you can easily solve each and every question, whatever you call. Okay, so the basic thing required is you have to understand the subject very basically. You have to understand each and every concept. Like from the basics today I'll start, and if you just study this first chapter very nicely, if you just study this chapter, I guarantee you each and every chapter coming after it will be really easy for you. And if you just devote some hours and spend some time with me, I guarantee you your all the marks in GATE examination and ESC, whatever exam you give for PSU's exams or interviews, you will be able to crack that exam in one go. Because this subject is the most important subject. Okay, so let's start today with properties of material and axial strength, which is our first chapter, and I'll just go by the basics. Okay, let's go. Okay, so to understand the strength of material topic, we have to first of all understand what is stress. Like I have been been seeing that a lot of students are pretty much confused about this basic thing only. They don't even know what is stress. So I'll ask you a basic question, what is stress? Okay, I'll give you a simple example. Let's take a simple example. If there is a body on a ground, for example, and this is a mass which is kept on it, and if I apply a force F like this, okay, so if this body is applied a force F, obviously it will move. It will move with an acceleration of A. For example, it is moving with an acceleration A. Okay, this is a body of mass M. So if we have applied the force F, obviously it will be moving. So if I ask you, what is the stress if this is a frictionless surface? If it is a frictionless, there is no friction. Frictionless surface. Okay, or it can be this like this surface if it is on a wheel. So obviously it will be a frictionless surface. The body is moving with, it is applied F and it is of mass M. So it is again moving with an acceleration F. So if I ask you that, what is the stress developed on this particular body? Can anyone tell me that? The answer is, there is no stress developed in this body. Why? This might be pretty much like new for students who are like taking up this subject for the first time. They might be thinking, why sir, why there is no stress? But actually there is no stress developed in this particular body. Why? Because what is stress? I will tell you today. Stress is something which is caused due to resistance. When you apply resistance to a body, when a force is applied on a body, and if you apply the resistance, the body applies the resistance, then there is stress developed. I'll give you a simple hint. If some person is coming to me and he is like pushing me, he's pushing me with his hands, and I am just not giving any resistance, I'm just going away. So am I applying any resistance? No. I'm moving with a certain acceleration or velocity, but I'm not moving with any particular resistance. I'm not providing any resistance. So the way to develop stress in a particular body is just by causing resistance to it. And how do you cause resistance? If a body now, again a man comes, he pushes me, now I'm not going. Now I'm not trying to move from my position. I'm just restraining him. I'm giving the resistance. So then there is stress developed. Then I'm getting the strain on my body. Then there is stress and then there is strain. So when I am offering resistance, then you will get the stress and then you will get the strain. So here, these bodies are moving with a particular amount of acceleration. So they are not offering any stress. So they are not offering any resistance. So there is no stress or strain developed in that particular body. Now, if there is a fixed support like this, and there is one body like this, and now if you try to pull this body with a force F, mind you, so what will happen? This support will say, no, you cannot move that body. You cannot move that body. So that will also apply a force F in this direction. So if you draw the free body, now if I cut this section here, so what will be if this will be cut into two parts, so this is a support, this is F. So if this is this part, so this will be also F. And from here to here, if I draw again, so this is the left part, and this is F, and this is F. So on this body, if I cut the section just after the support, this is the free body diagram. If you just capsulate these two together, so what will happen? These two forces F will cancel because these are internal forces. These two will cancel out each other and we will be having net force, this diagram. Okay, so actually you will see that this body is having two forces F in this direction. So this is balanced by this force and these are generating stress. And that's why there is strain in the body and that's why there is deformation. So that's how you cause stress in a particular body and that's how you generate some amount of strain in a body. Okay, so that was basic thing about stress and strain. Okay students, now let's discuss what are the different types of stresses which a body can face. So we all know that there can be two different types of stresses which can be generated in a particular body. What are these? Let's see. If this is a three-dimensional body which I am taking up, okay, so if I just consider this surface over here, there can be two different types of forces which can be, with two different types of stresses which can be acting. One is the normal stress sigma and another is the axial stress tau. So these are the two different stresses which a body can take. Now these stresses are generated due to forces. The forces can be of any type. Now we do not have any knowledge about force. We know that only stresses are developed and these are of two types, and the forces can be anything, any moment, any loading, any type of loading. Wherever you apply, that will generate two types of stresses. One is normal to the body, like this, sigma. This is called as the normal stress. And this is tau, which is shear stress. Okay, so these are the two different types of stresses which can be developed in a particular body. Okay. students, now let's look at the types of forces which a body can take up. Now this is a diagram, this is a 3D diagram which I have been showing over here, and here there is the all types of forces which can be applied on this particular body. So let's look that what are the different types of forces which can be applied on the body. So firstly, here is a force which is Fx. This is in this normal to this particular plane, and this is going directly towards the central point. So this is directly normally acting on this particular surface. Now this Fy is on the plane, this plane only, this is on the plane, and this Fz is also on this plane. So this, let's call this is one plane, and therefore this Fx is normally acting on the plane, this Fy is acting on the surface, and this Fz is also acting on the surface. Now let's look at the three moments which have been put up here. What are different types of moments? First, let's see this Mz. What is this Mz actually? This is nothing but the bending moment which is bending the system like this. This is applying bending. So due to this surface will bend like this, isn't it? This will cause the bending. The surface will bend like this. If it is straight like that, this will bend because of this bending moment. Now similarly, I'm just talking about this particular surface. Mind you, just this surface. Just look at this surface. What is happening to this particular surface? Now this, once again I'll tell you that this moment is causing the bending moment of the surface. So this will bend like this. Similarly, this My is causing the bending of this surface like this. It is bending it like this. If this is the surface, so it is bending like this. Inside like that. This is bending like this due to Mz, and My is bending it like this. Now let's see what this Mx is doing. What is Mx doing? Mx is actually putting up like this. It is actually movement like this which is twisting the surface, which is not bending, it is twisting. You can see here it is twisting. So if it is twisting like this surface is twisting like this. So it is revolving. It is not bending, it is revolving around a particular plane, and that's why that is a twisting moment, Mx. So how will you see the direction? Why I have put up Mz? Because if I roll my fingers, this my thumb will show the direction of the movement. So that's why this Mz is coming out here. So that's why this Mz is a bending moment. Okay, this bend Mz is nothing but a bending moment. Similarly, this My is also causing bending in this particular direction. If this is A, this is B. So this My is causing the bending about this plane. This plane is kept constant, and these two will flap together, will bend. And this Mz is causing around CD direction. It is bending the plane in that particular direction. And this Mx is actually twisting the system. It is actually twisting the surface. So that is called as a twisting movement. So you have to be very careful that what is causing bending and what is causing twisting. Okay, so which moments, if you are very clear, I guess you are all very clear that which are the forces which are causing bending and which are the forces which are causing twisting. Okay, so now how to test the direction? I told you, if you roll your fingers, these fingers around this line, so the thumb will show the direction of movement. That's why this is Mz. Similarly, if I roll around this direction, this moment My, so this is going in Y direction because this is my plus Y direction, this is my plus Z direction, and this is my plus X direction. So my fingers, if I'm rolling my fingers like this, so this thumb is showing what? The direction, and this Y is nothing but the direction of the bending moment. You have to be very clear about what is the direction, what is the bending moment actually causing. It is causing twisting or the bending. You are very much clear about it. So let's write down what are different forces which I have been writing up. So firstly, what is Fx? So let's write out. Fx is actually a normal force which is acting on the surface. So Fx is actually what? It is a normal force. Okay. Now, what is Fx actually causing? Normal force will cause a normal stress sigma because it is causing a normal stress. That's it. Very, very easy to understand. A normal force will always, each and every time, cause a normal stress on a particular system. So this Fx is a normal force. Now, if I see this Fy, what is this? This Fy is actually shearing the surface. Whenever the forces are acting on a particular plane, it actually shears it. So shearing force is nothing but our Fy. So Fy is what? Fy is actually shear force. Okay? Now, what is this Fz? Again, Fz is acting on the plane only. So whenever there is a force, I told you that it's acting on the plane, that will cause a shear force. So Fz is what? Fz is actually the shear force again. Okay, now Mx, I already told you, Mx is a bending moment. Okay, Mx is a bending moment as it is causing the bending about which plane? This AB plane. I told you this will bend the plane like this. This plane is there, so it will bend like this. And this plane is, due to My, is also bending about this CD plane. So you are, this AB plane, you are bending about My, and CD is bending about Mz. Very, very easy to understand with this diagram. So My is actually again a bending moment. Now finally, the most important thing, Mx, what is it actually causing? It was actually causing what? The twisting moment. It is nothing but, it is causing the surface to twist. What is twist? See, I'll tell you the difference. See, if anything, for example, this is the surface. So if I just see this, if this is a body. So if I'm twisting it like this, so it will bend like this. So but when I apply this shearing thing, so it will twist. The hands will twist it. So this is causing twisting moment, and My is nothing but the bending moment. So over here, Mx is nothing but the twisting moment. Now, these are the forces. Now I'll write down what these forces are actually causing. Okay, so let's write down here, what is the normal force causing? The normal force causes the normal stress. So due to normal force, normal stress is generated. And what is this? So it is nothing but generating what? This is what it is generating. It is generating sigma. Due to normal force, normal stress is generated, that is sigma. Shear force will always generate what? Easy to understand, that will generate what? Shear stress. Very easy to understand. So that will generate shear stress tau. Okay, again this is a shear force, so this will again generate tau. Now, bending moment, what is it actually doing? It is actually hitting the surface like that. If you hit the moment like this, what is it actually hitting it? Like this. This is the hit which is providing on the surface. So what will it call? Absolutely, that will again cause the normal, what the normal force was causing, and that will just cause the bending stress, or as the bending moment will just cause the bending stress, and that is nothing but the normal stress only, sigma. That will be just like a normal hit which will be acting on the surface, and that's why it will be again causing sigma only. So again bending moment will cause sigma, and always twisting moment is on the surface. It twists the surface. So this surface is twisted, and that's why this is like that. It twists the surface, and that's why it creates the shear on the surface. So always note down that twisting moment causes shear of a surface. So whenever you are providing twist on a surface, it will twist along its surface and will cause twisting moment, will cause shear stress. Okay, so bending moment will cause bending stress, that is nothing but a normal stress. Bending moment always bends normally along the plane, so it hits the moment like that. So that's why this will cause nothing but the shear stress. Okay, so I hope these things are clear. These are the basic things which every engineer should know. Every engineer. This you would be learning in your engineering mechanics also. A general engineer should know all these things, and basically the mechanical and civil engineers should know these concepts, because this is the basics of mechanics which each and every student should know. Okay? Okay students, now let's discuss what is actually a 2D structure and force. How we say that, okay, let's discuss this system as a 2D system only. Why we discuss as a 2D system? Because discussing or finding out the values of a 2D system is pretty much very easy. Why? Because when there is a 3D system, to study all different types of forces becomes very difficult. How many different types of forces there were? There was Fx, Fy, Fz, Mx, My, Mz, 6 different types of forces or loading conditions you may call it. So there were different kinds of loading on the surface. So studying that particular system becomes very difficult. So how do we study a system in general? We study a 2D structure and force system. And what is a 2D structure and force system? There is very confusion among the students. So today I'll clear your this problem that what is a 2D system actually. So a 2D system is nothing but when the force and the moment, different kinds of force, different types of moments which are acting on a particular body can all be encapsulated or presented on a particular plane. So on this plane, Fx, Fy and Mz are acting. Okay, so if I keep these forces on this particular plane, I can shift these forces, and all 3 forces will be just on this particular plane. So Fy is on this plane only, Fy. Fx will be also standing on this plane. And this Mz will also be on this plane only. So this plane is carrying, or we can say that it is holding together all these three forces, and that's why this is nothing but a 2D structure and two-dimensional force condition. So when are you saying that this is a 2D system? When all these three forces can be taken together and presented on a particular plane. So these forces were acting on this plane. Do not get confused. This is different plane, and this is a plane which I have just taken an imaginary plane which will be passing through the system, and we can just keep these three forces because Mz is acting like this. Because this is like this, so direction is like this. So these forces can be easily kept on this plane. See my hand very carefully. This is the Mz, so this is the direction. So this can be easily kept, this moment can be easily kept on this plane. So that's why all these forces, this Fx also like this is the loading. See, this can directly be kept on this particular plane, and that's why this is a two-dimensional structure or a 2D theory which we study about stresses. Thank you. Okay students, now let's try to understand the basic concept of the stress components. Here we'll be discussing there were what? Two types of stresses. What were these? One was the stress which was normal stress and other was what? Shear stress. So today we'll be discussing that what are the different types of stress components which may we have. So these are nothing but the normal stresses and the shear stresses, and out of that we can also component them. We can also divide them in different types of component. So let's see that this is a positive X plane. Let's call this as a positive X plane. So the back side of that would be what? The negative X plane. Okay. Similarly, this is what? Positive Y plane. So the bottom portion will be what? The negative Y plane. Similarly, this is our positive Z plane. So opposite side of it is what? Negative Z plane. Okay. So I am simply writing sigma xx over here. So why are we writing sigma xx? That is very, very important. How do you write sigma xx? Why? Because there are two components, first letter, second letter. Similarly for tau, first letter, second letter. What is first letter representing? The first letter here is representing the plane which is it acting on. What is this sigma xx acting on? This is acting on this plane, this particular plane. This is the positive X plane I told you. So that's why this is the positive X plane, and that's why this first letter is coming as X, because it is acting on which plane? X. And what is the direction? X. So that's why here first letter is denoting what? The plane it is acting on, and second one is denoting what is the direction it is on. Similarly, the tau xy. See here, what is the plane it is acting on? This is acting on this plane. I told you this plane is what? This plane. This plane is the X plane. So that's why the first letter over here is what? That is X. Second letter I told you, the direction. So here, that's why this is in which direction? Y direction. So that's why the word comes here, tau xy. Again, now let's see this one. Tau xz. What is it actually? This is acting on X plane, isn't it? The first letter I told you. First letter denotes the plane which is it acting on, P, and the second letter denotes the direction. So P, D. So what is this plane acting on? This tau xz is acting on which plane? X plane. So that's our first letter, X, tau x. Which direction it is coming on? This is coming in Z direction. This is my Y, this is my X direction, and this is my Z direction. This is my Z direction, this is my X direction. And that's why this is coming as the XYZ direction, and that's why you get first letter as the plane and second letter as the direction. Very, very simple. Student gets confused at what is actually happening. This is pretty much simple. So what I can again do is, here on this plane also I can check. There can be what? This will be the normal stress, sigma. Sigma is always the normal stress. So sigma, what is acting on? This is acting on the positive Y plane. So first letter again, Y. What will be the second letter? Which direction it is on? Y. Positive Y. So that's why this is sigma Y. Sigma Y, because sigma is the normal stress. Normal force will cause what? Normal stress. So very, very important that what is the direction. Now again, let's go. So in this direction, for example, if there is some stress, so that is in this plane, so obviously which type of force it will be? Shear force. That will cause what? Shear stress. So what will you denote? Tau. Now let's look at the direction. What direction will it be? This is the direction in X direction, but what plane is it? Again, this is on the Y plane, so this will be Y, and which direction it is? X. So that's why this will be tau yx. Now, what is this thing? Again on the plane, on this plane only, what will be the definition? That will be nothing but tau, because on the surface there is shear force that will cause shear stress. That's why the word tau. Now, what is the direction again? Tell me, which direction it is? Z. But what is the plane it is acting on? Y. So first letter always plane. So Y and Z. Similarly, you can do for Z direction as well. This is very simple nomenclature I told you, which you will be using throughout this chapter. These are what? These are stress components. See here. Have I used any other thing apart from normal stress and shear stress? No. These are shear stress and normal stress only, but these are the components. Like you would have used now vectors. Vectors you would have studied in your 12th standard. So if a force F is acting here, so what are the two components? Here this is theta, this is F cos theta, and this is F sin theta. So you do the balancing of the force. Do you? Yes. So similarly, the balancing of stresses is also done. That this stress is nomenclated as like this sigma xs, sigma yy, sigma zz, depending upon the plane which it is acting on and the direction which it is acted upon. Okay? Okay students, let's look at the topic of equality of shear stresses. We all have seen that lot of time I have seen given you tau xy and tau yx. Last diagram we saw that there were tau xy and tau yx. Now we all know that and everyone has told us that take tau xy equal to tau yx, but we do not know why is that actually coming from and where it is actually looking forward to. So now let's see today that how actually these two forces on adjacent plane and opposite plane become equal. So here we will be studying equality of shear stresses. Okay, now let me make you clear that you cannot equate stresses or you cannot have resultant of stresses. Someone tells you that if there is tau here and sigma here, you will make a resultant of tau square plus sigma square under root, that is the resultant of, you can call it as resultant stress. Resultant stress, that is completely wrong. That is not the way to do. This is not force. You can always equate and you can always resolve and you can always find the resultant of forces but not stresses. Stress is not a force. Stress is a system which is a resisting thing. So that is not a force, so you cannot apply these things on that. How can you do it? First you have to convert the stress into a force and then you can use these equilibrium and the resultant conditions. Okay, so let's see how are we actually finding out these things. So as I am seeing that this system is in equilibrium, isn't it? It is in equilibrium because it is not moving. It is not moving with any acceleration. So this is moving, not moving at all. So if it have moving with constant velocity also, then also it would have been in equilibrium. But this is not moving at all. This is in rest condition. That's why we can apply the Newton law. Newton law of forces. We can use summation Fx equal to 0 and summation Fy equal to 0. So if we do summation Fy equal to 0, what are we getting? Fy is tau 1 and tau 4 direction. These are the two forces which will be acting. But I told you tau is not a force. First you have to convert that into what? This is a stress. So you have to convert into force. How will you convert? This is a stress which is acting on which plane? This particular plane. And what is the area of this plane? B into C. So first you will multiply. What is stress? Stress is force by area. So force by area into area will give you what? Force. So similarly, if you multiply tau 1 into BC, okay? So if you multiply tau 1 into BC, you will get what? This force in this direction, and that will be what? Equal to, because this is in equilibrium, so this will be minus tau 4. And tau 4 is actually acting on this plane only. So this is one more plane, this is another plane. So these two planes are similar. Both of the dimension is what? B and C only. So tau 4 into BC will be what? That will be also giving you a particular force. So both of these equated to 0. Because that is what actually is happening, because the system is in what? It is in equilibrium. So if you just do it, so what will happen? This BC will be getting cancelled. So tau 1 will come as tau 4. So this is what you get because of equilibrium conditions. And that's why tau 1 becomes equal to tau 4. So what did we get? We got that forces on opposite faces are equal if they are acting in different directions. This stress was acting in this direction and this was acting in this particular direction. Okay, now if I equate this to also, if I do summation Fx equal to 0, what am I going to get? See, this will be tau 2 into AC, tau 2 into AC minus tau 3 into what is the area which it is acting? It is again acting on A and C only. Okay, very easy. So what will be that particular thing? That will be also AC only, the area which is acting. So this will be also again equated to what? 0. So again AC will get cancelled and tau 2 will be now again equal to tau 3. Understood? Very important that forces on opposite planes and acting on opposite directions. Yes, they will act on opposite directions. These are what? Shear stresses. All are tau. These are acting on the plane. Shear forces cause what? Shear stresses, and they are equal because they have to be equal in order to satisfy Newton's law, and that is equilibrium conditions. Okay? Now, let's try to prove one more thing over here. What we can prove is, like, if we try to take the moment at this point, O. So, if I try to take the moment at this point O, these tau 3 and tau 4 will pass through it. So, their moment will be 0. So, only tau 1 and tau 2 will cause their moments. So, let's check how the moment is actually calculated on this particular point. So, this moment will be calculated as tau 1 force. First we have to make it a force. So tau 1 into BC and this will be multiplied by what? This is a force and multiplied by this distance. So this will be A, and this is tau 2. This will be subtracted from what? Tau 2, and tau 2 into AC. Tau 2 into AC, and that is, what is the distance from this point, this force, this distance? What is this perpendicular distance? Here BC was the area and A was the distance, and here AC is the area and B is the distance, and the direction both are causing are what? Opposite. This is causing what direction? See here, this is causing anti-clockwise movement, and this tau 2 is causing what? Clockwise movement. Both are opposite, that's why the negative sign, and this should be what? Equal to 0. Why? Because the system is in equilibrium. It is not all, it is also in rotational equilibrium, also in translational equilibrium. So due to rotational equilibrium, you will get the value as tau 1 is equal to tau 2. And this again gives us a very significant result that is used always, that stresses, which stresses? Shear stresses on adjacent plane are equal and pointing towards each other. Okay? Pointing towards each other. Now if I take the moment at this point P, so tau 1 and tau 2 will cancel out each other. So let's see what we will get. Let's see what we will get. If I take this moment about this point, again I'll get what? I'll have tau 4 into, what is the area which is it acting on? It is acting on, this is the perpendicular B and this is C. So tau 4 into BC is the area, and what is the distance? A. And this tau 3 will be in opposite as this is causing anti-clockwise, this is causing clockwise. So that's why negative. Tau 3 into what? This is the area is AC, and area is the AC, and what is the distance? That is the distance is B. So again these two will get cancelled and you'll get tau 4 equal to tau 3. Now if I take moment about this point, let's call this point as, for example, you can call this as OP, this can be Q, this can be R. So if you take the moment about Q, you will get that tau 1 and tau 3 are equal. Again you will get, because this will cause what? Anti-clockwise movement, this will cause clockwise movement. So you will also get what? Tau 3 is equal to tau 1, and you will also get another thing, that you will also get this thing. Tau 2 is also equal to tau 4. Okay, so this all four conditions will be easily satisfied. So what are the two things which we got from here? The two things are shear stress acting on two different adjacent planes are equal, and sometimes they are pointing towards each other, sometimes they are pointing away from each other. Tau 1 and tau 3 are moving away from each other, they are also equal, and tau 1 and tau 2 are also equal. Because why? Because these are also moving towards each other, and from the equilibrium condition we know that tau 1 equal to tau 4, so from there also we can find out the same thing. Okay, so this was basically the equality of shear stress. Hope you understood it very, very carefully. Okay students, let's discuss the Hooke's law. You have always heard from your 11th 12th standard that Hooke's law. And what is Hooke's law? That everyone knows that stress is proportional to strain. So that's what you get, that stress divided by strain is a proportionality constant E that you get from dividing the stress and strain values. That is nothing but called as the modulus of elasticity also. Now, this is a stress. When every time this is defined, the Hooke's law is defined, there are two definitions which are left. Like the two definitions, along with it should be said that it is also defined only for homogeneous and isotropic bodies. What is homogeneous body? What is isotropic body? You need to take care of. What is a homogeneous body? Homogeneous means that each and every block should be same, exactly same carbon copy should be there. So as you can see that all these blocks are same, so that's why this is a homogeneous body. Here you can see that these are also homogeneous body. Why? Because each and every rectangle here is same. You can say that each and every rectangle is same. So same to same, each and every rectangle is same. So when the building blocks or any building microorganism of any particular body. So my body is made of simple cells. So these are different simple cells. So if I say that my body is homogeneous, that means all the cells should be equal and everything should be same. So similarly here, this each and every cell is same, and here also each and every cell is same. So that's why these two are homogeneous bodies. Now, isotropic means that the properties in different directions do not change. So if I move in this direction, so if I go in this direction, I get this particular length. And if I go in this direction, I get same length. So this x is equal to x. But what is happening over here is that this is, for example, A. So this is not A, this is B. So as you can see that properties are changing in different directions. So that's why this is not an isotropic body. So that's why it is Hooke's law is not valid for this body. For Hooke's law to be valid, there should be similarity in all directions, and that's why we say that it should be an isotropic body. What is an isotropic body? Is that the properties in different directions are same. Okay? Okay students, so now let's look at the deformation of a member under axial load. So how is the deformation of a member under axial load? That is very, very important. See here. So like these are the type of questions which are asked in GATE and IES day in day out. Like every year you'll find 2 or 3 questions based on this topic only. Simple application of the formula or the concept, you'll find plenty of questions on this particular topic. So how are you going to use this thing? That is very, very important. See here. If I apply a load P in an axial bar, first of all, will there be any stress generation? Yes. Why? Because there is a restraining force which will be generated due to this support. The support will try to pull back the body and will be keeping it in contention, and therefore there will be generation of stress in the body. So how will you generate stress? So P will be a load, the load P will be acting in this direction and this will be kept like that. So there will be stress generation. So sigma is equal to P by A and epsilon will be equal to delta L by L. So now if I try to do something over here, so what will happen? That you can easily get that P. So if here P is acting, so what will you get? Here. Now sigma is equal to, stress is equal to E into strain. Stress is equal to E into strain. So what will you get? You will get that P by A is equal to E into delta L by L. And you can easily find that your delta L will be equal to PL upon AE. So delta L will be equal to PL by AE. So this is how you find the formula of delta L, which is nothing but the change in the length. So delta L is easily calculated by this method, PL upon AE. Thank you. Okay students, now we have to find out the total deformation of this particular body. What is the total deformation of this body? Can anyone tell me? That will be nothing but a net change in this direction. So if this is a body and this is moving like this, so what can be that? That will be the net change in this body. So obviously there is no restraint. So these forces are restraining themselves. So this P2 might be balanced by some part of P1. This P3 might be balanced by some part of P2. And that will cause axial strain in the bodies. And this net system will get tensile or compressed depending upon the loading which it is acting upon. So we will simply calculate the net deformation in the body by simply using simple connected members. So if I see that this is a member, this is a member, this is another member, this is another member. So I'll try to bisect or cut down my member where there is change of loading. First I have to see where there is change of loading. And secondly, I have to see the change in material. So the change in material can be anything of A or E values. Okay, so generally we see the sections over here when then the area is changing or the system is changing the area. We generally, this is basically based upon area only, the change in area of the member. We'll just try to shift or try to calculate that value differently. So let's see how can we easily calculate the deformation on this particular body. So if I see this material DE, so firstly I need to calculate the net change, the net delta. That is nothing but the delta. So what is that? Delta will be nothing but equal to delta between what? Points A and E. Okay, and that will be nothing but equal to delta DE plus delta CD plus delta BC plus delta AB. Now what you need to keep in mind is if you're saying that net change is tensile, so each and every member here should be taken as a tensile member, or you should say that every material in this system is getting tension. So if you're saying that way, maybe that is causing compression, but that will come negative, no issues. You have to follow particular convention that, okay, let's try to take that this is causing a system as a tension member. So this is getting only tension. So we'll say that, okay, for example, our answer comes as negative. So whatever we would have taken in the initial case, that is just coming the opposite. And then we'll say that, okay, this is compression now. Okay, so let's start. How are we going to calculate the net delta? Okay, so this member here, this is a member DE. So here there will be a force P1. Okay, so this is a force P1. Obviously each and every material is in equilibrium. So if this is P1 force is acting, so this side also P1 force will act. So this will be balanced by P1. There is at the junction we have P2. So what I have done is I have just cut to the left, sorry, to the right of P2. I am taking that section only. So when I cut this thing over here just to the left, just to the right, so this will be this system which I have taken. So there the P2 will not come. So there will be only P1 forces in this direction. So there will be P1 will be balanced by P1 over here, and the net force on the system will be zero, obviously, because it is in equilibrium, and the stress will be generated only due to P1 here. Now if I just go at this system, this one CD part, so what I'll see is first of all this P1 should be balanced. So this P1, when we combine, this P1 should get combined because this is an internal force, this should get cancelled up. So P1 should be balanced like this. Okay, so P1 will be balanced. This is my DE part, and this I am taking my CD part. So first of all, this P1 should be balanced over here. Now put up the section. Now what is the force acting on this particular section? P2. Now put up that force, because now I am considering up till which point? Just to the right of this thing. See. Okay, so now I have cut this and just have put on over here. So what I'll see that P2 will be acting, P3 will not be acting, because P3 is just acting to the left and the section I have taken is just to the right. So P1 plus this will be P2 will also come over here. Now again this system should be in equilibrium, so that's why to balance this P1 and P2 we need a force which is equal in the magnitude but opposite in direction. So this is P1 and P2 acting in this body in this direction, so we'll be needing what? P1 plus P2 here. So again this thing is in equilibrium, and that's why there will be a force which will be generated P1 plus P2 in this direction, P1 plus P2 in this direction. So this will be causing tension. At this point of time, I don't know whether there is tension on compression. If the thing comes out to be positive, obviously I am correct, but if it is coming negative, I was wrong, but my convention was wrong, my theorem was not wrong. So that's why this is the system, and this is how you're going to approach these type of problems. This is the most asked topic in GATE Civil Engineering, ES, and also Mechanical Engineering, GATE and ES. Okay, so please understand this topic very, very carefully, because a lot of students gets confused because what is the direction and the convention which you should take. So this is the thing and the basic thing which is required to solve these type of problems. Okay, now again, if I take this thing, this one BC, this was my CD part, so let's take this part, CD part, BC part. Okay, first of all, what will you do? You'll just balance this, because when you encapsulate all things together, internal forces should balance out. P1 should get balanced by this P1, and only P2 should be left over here at this junction. Now when I cut this section over here, so what should be there? First of all, this P1 and P2 should be balanced. So this, when I encapsulate and bring these two together, P1 plus P2 should be balanced, and only P3 should be acting over here. Okay, you can see when I just take these two together, P1 plus P2 will be cancelled by P1 plus P2. When you combine all these together, internal forces cancel out, and only the forces which are acting at this point are left. That is very, very easy to understand. Now what is the force or net force acting in this direction is what? P1 plus P2 plus P3. So what will be the force acting in this direction? P1 plus P2 plus P3. Now let's take up the final one, which is that this is the AB part. So what is happening in AB part? In AB part, you can very well understand that there are only these three forces acting, because there is no forces at this junction. And what will you write down? You will write down here P1 plus P2 plus P3, and that will be balanced by what? Once again, P1 plus P2 plus P3, because net system should be balanced. Now you will find that very, very important thing out there. I'll tell you. Now if I just look at this system, the system is in equilibrium. Just look at this system over here. What will you say? What will you say over here? That we will say that net force P1 and P2 and P3 are in that direction. So that is what you are getting actually over here. So that is what we need to, if this is a P2 in this direction, so if this is a P2 is in this direction, so what will you get? You will get the net system is what? P1, P2, P3 and P4. So you can easily get that the system is in equilibrium. Okay, so how will you find out the delta? You'll simply add on the values. P1 is acting on this system, so P1 L1 upon A1 E1, and simply here it will be P2 P1 plus P2 into L2 upon A1 E2. Now we'll take up one problem that you can easily solve these problems, and we'll also look at the statically indeterminate part later on. Okay. Okay students, let's try to understand what is a statically indeterminate beam. Now this word is very haunting to all civil engineering and mechanical engineering students, because always they are confused that, sir, tell me what is indeterminate system, what is determinate system. So let's try to clear this concept today. See, indeterminate means, the word itself is saying indeterminate, the thing which cannot be found out by simple calculations. See, if I try to find out, if I look at this problem, so there is a force P acting at the center, not the center actually, at A distance from this end and B distance from this end. Now, what is happening on this beam is, there is a force acting P on this particular point, and there will be some reactions generated. Very well, you know that there will be some reaction RC, and there will be another reaction RA. So there will be two reactions that will be generated in the system. So you need to calculate that reactions. So how many unknowns you have? You have two unknowns. And how many equilibrium equations you have? Only one. That is summation fx equal to 0. So one equation, two variables. Cannot find out both the variables. So how do you calculate that particular thing? You need a magical formula or a magical theorem. And what is that magical theorem? That is nothing but the deformation or constraint equations, the deformation equations. Here we had the knowledge about deformations. The net change was what? PL upon AE in a system. So if we add on all the PL upon AE, we'll get the net deformations. But as this system is fixed on both sides, can it have any amount of deformations? No, there would not be any deformation in the system. So what we got? We got a compatibility or constraint equation, and that is nothing but equal to delta equal to 0. What is that delta? The net delta. The net change in delta in this system is 0. So what will you say? So I can write down that net delta is equal to 0, and that is nothing but delta AB plus delta BC is equal to 0. So net delta is 0. So we can equate this, and one equation we already have. What is that equation? We know that P is equal to RA plus RC. This is one equation. So we have one equation, P is equal to RA plus RC, and one equation is delta AB plus delta BC is equal to 0. Now can you find out the value of RA and RC? That's the thing. So let's try to find out the value of RA and RC. So first let us consider this part, BC. So what is happening in BC? See, there is a force which is acting like this. RC is trying to compress that particular body. So people will say that, sir, this RC is the support reaction. Why is the force coming here? So let's try to understand why this force is directly coming up over here. So if I cut this section just to the left of this, so what will happen? There will be this support thing, and RC is the support reaction over here. So that will be balanced by this. This should be balanced. The support just cut. There is a cut part. Just the body is having just small cut over there. So this should be balanced with RC, and this should be again this force. If you come over here, so again RC should be balanced because this is a part. So when you combine both of these together, RC and this RC will cancel out, and net system will be like this. So that's why this gets transferred from here to here and from here to here. So that is how the forces get transferred, and you can see over here, if RC is the reaction, directly you will transfer the load RC over there. Just see that when you combine everything together, the internal forces cancel out each other and only external force is seen. Can you see internal forces in my body? My body is having a lot of joints in it, isn't it? And there are a lot of force transfer in the body. Can you see? No. Only you can see my weight and what I am providing to the ground, and ground is providing me normal reaction. So similarly in the body, you cannot see internal forces, and you can only see RC, P and RA. Okay? So if this is RC over here, now where should I cut? I have just seen cut this section, and just to the right of this I'll cut. So I will not get P force. The P force will not be acting. So only RC will be acting over here. Okay, now in this part, what is happening? In this part, first you will balance this RC over there. This RC is balanced now. This RC is balanced, but there is also force P coming out in this direction. So RC is in this direction and P is in this direction. So what will you get? You will get, if I just see I have written compression, so I'll take compression only. When I have just gone with compression here, so I have to write compression system on this thing. So what is the net compression? RC minus P. So in this direction it will be getting compressed by what? RC minus P. As you can see that this RC will be balanced by this one and this will be balanced by this P. So this is the net compression in this direction. Why? Because this is net is what? RC minus P in this direction. So that's why this has to be in this direction with RC minus P. So that's why this system is having a loading of RC minus P. This system is having a load of RC. So what you will get? You will get what? Very, very easy to find out that RC. So now net system is what? Delta of this plus delta of this. So delta of AB, net delta is 0, we know that. So delta of AB plus delta of BC is equal to 0. Don't worry about the sign. If you are taking tensile of delta AB, take tensile of delta BC. If you are taking compression of AB, take compression in this and use plus sign over here. So what is the compression of BC? BC will be what? RC into B upon A and E are same for both. Okay, plus what is this? This is nothing but RC minus P upon AE into A, and that is equal to 0. This and this will get cancelled and you will get RC value. What is the RC value you are getting? RC you are just getting as RC is equal to P into A upon A plus B. This is a very, very important equation which we have come on, and this is the very, very important formula which people by heart. Why to by heart when you know the concepts? Just have to simply do this thing and you can get these formulas very, very easily. Now you can similarly get RA. RA will be nothing but what? RA will be nothing but equal to P minus RC, and that is nothing but PA upon A plus B, and that will be equal to B upon A plus B. So this is my RA value. So I got both RC and RA by simply using two formulas. One was the net Fx equal to 0 and Fy equal to 0. Fy is not there because there is no force in vertical direction. So from Fx equal to 0 we got P is equal to RA plus RC. Here also you can get that P is equal to R. This RC minus P is equal to this thing. So you can get from that also, but no need of that. You can simply use these equations and you will get what? The two desired results. So that is how you need to use the theorem, and you have to go by the concepts, and simply you can use the loading conditions to easily calculate what? That is what which is required, that simply P is equal to RA plus RC and RC is equal to PA upon A plus B and RA equal to PB upon A plus B. One thing we can easily calculate is, what is that? RA is coming as P into the opposite distance upon net distance. Similarly for RC, P into this distance upon total distance. This you can remember, but I will recommend you not to remember formulas in SOM, because SOM is totally conceptual subject, and if you go by the concepts, you can very well do in this subjects. Okay? Okay students, let's solve a very typical problem which is a previous year's IES and GATE problem in civil engineering. Okay, this type of questions is asked every year in GATE and IES, and this is the basic concept which we'll be using of statically indeterminate beams and to solve the problem. So that what are we requiring? We are requiring RA and RD values. Now this is a very simple question which is given to us. We have to just use basic things to calculate this RA and RD value. Now I told you that whenever there is a system which is indeterminate and you have to calculate the value of the reaction supports, you have simple equilibrium equations. That is only one equilibrium equation you have. What is the equilibrium equation you have over here? If I take RA and RD in this direction, so I'll have one and only one equilibrium equations. I can write down that. Okay, let's write down that. What is that equilibrium equation which we know that? We know that RA plus RD plus P plus 2P minus 3P is equal to 0. That means RA plus RD is equal to minus of P. Okay, this is my equilibrium equation and this is what I have got over here. Now this is the one equation I have. Now another equation I will be getting from the compatibility equation or the deformation equation or the constraint equation. All three things are same. So we'll use that compatibility equation. That is nothing but the deformation theorem, that the deformation becomes 0 in a statically indeterminate thing. Why? Because both the supports are there and the support is not yielding. So yielding of support problem can be also taken where the support yields. Means that support is not resistant enough to hold the loadings. So what will happen? The support will move from here to here. So what is the main thing here? That is not a typical problem. This is a simple problem. So let's see and try to proceed this problem. So I told you that first thing you need to keep in mind is that this body and this body and this body, all four bodies are taken. Why? Because firstly, at this point there is change in area. Again, this point there is change in area as well as change in loading. Here there is change in area and change in loading because 2P is acting at this junction. Here there is change in loading only. So therefore we have four cross sections which will be taking, and therefore four bodies will be taken. We will be calculating all the four deformations for these bodies and summing it up to 0. From there we can get the RA or RD value, and then we will find out both the values. Okay, so let's proceed this question of IES and GATE, which is a very typical problem to some students but very easy for few who know the concepts very well, and today we'll learn this concept to the core. Okay, let's move forward. So if I take this body, so here RD will be acting. Okay, to balance RD again you will be applying an RD force over there. Okay, now you will cut down this system up till this point, just to the right of this point. Now again you will take up this body and you will cut down over here just to the right. So what you will get? You will have, firstly for balancing RD you will keep RD. Okay, and then at this junction there is 3P. So 3P is coming inwards. So you will apply 3P inwards. Okay, now what is the net tensile to the system? Net tensile movement is in this direction. RD minus 3P in this direction. So to balance that, RD minus 3P should come in this direction as well. So here also you will have RD minus 3P. Okay, now you will cut this system here. Now again you will take up this system. Now firstly you will balance this RD minus 3P with, this is going outward, so you also take this one here. So this will be balancing out together. So RD minus 3P first I will write down. Now is there any force at this junction? Yes, there is. What is the force at this junction? 2P. So you'll write down this 2P over here. Okay, and you have cut just to the right of this, so this P will not be incorporated. Now, so what is happening? RD minus 3P there and 2P away. So this will be what? RD minus just P. So if you sum up both these together, you will get RD minus P in this direction. So you have to balance with RD minus P in this direction. So what is that? RD minus P. Okay. Now you take this part, the final part. What will you write down? You will write down here RD minus P here. Okay, and then you will add what? You will add the P, which it is acting over here. So this will be just here P. So what are you getting here? You are getting just RD minus P plus P, that is RD only. So what are you getting? You are getting RD in this particular direction. So, sorry here, this, if you sum up, what are you getting? RA plus RD was coming out to be 0. Okay. So now, this is a very simple thing what you have written. So this is a simple concept which we'll be using now. Now RD minus P plus P, and this is RD. So this is the system and the scenario is like this. Now we'll calculate the net delta. Let's see how will we calculate the net delta. So the net delta will be nothing but, so let's see what is there in this thing. This is having PL by AE. So what is P for this thing? RD. And what is L? That is L only. And what is A? That is 3A. And E, PL upon AE. Okay, now we'll sum up with plus. That will be for this part. So this will be again 10. We have all we have taken as tension. So no need to worry about direction. We have taken all in tension direction. Just put it as it is. Okay. So here for this, the net tension is what? RD minus 3P. This away from here and away from here. So RD minus 3P. And what is the L for that? That is nothing but L only. And what is the A? That is A only. And what is the E? That is E only. E for all is same material, so E for all is same. Okay. So now for this body, what is the thing? For this body you will say what is the force? Net force? Net force is what? RD minus P. So RD minus P into L upon 2A into E. Now plus, finally for this thing, you will say that, what is that? RD into L upon 2A into E. And this all four summing together is nothing but equal to 0. Why? Because net delta is 0 as it is a statically indeterminate problem. These are between fixed supports. So you need to find out the delta and you can equate it to 0. So that is what I have done. I have equated the whole system to 0 value. And that is what we need to do when there is a statically indeterminate system and these are between two fixed supports. Okay. So what will you do? You will cancel out the A thing. Okay, the A and L also will get cancelled out. It will be going because that side. So now what I'm having is, if I write down over here, what I'm getting is RD by 3 plus RD minus 3P plus RD by 2 minus P by 2 plus RD by 2. Okay, this is what I'm having right now. So what I'm getting is RD and this RD by 2 becomes RD. So this will be nothing but 4RD by 3. Sorry, RD by 3 plus 2RD. So RD by 3 plus 2RD will be RD by 3 plus 2RD will be equal to 3P plus P by 2. So that will be nothing but our 7RD by 3. 7RD by 3 will be equal to what? 7P by 2. So now what I'm getting is RD is equal to 3P by 2. That is the relationship which I have got here, and that is the most significant relationship which I have got, and this is how I have solved my problem going forward. This is RD is equal to 3P by 2. Okay, now I got my RD is equal to 3P by 2. From here I know that RA is equal to minus of RD, so my RA will come down as minus of 3P by 2. So this is how I have solved both my reactions, and these are the two reactions which I needed to calculate in the initial stage. Okay, so this is how you move forward slowly and simply. This is a 2 marks question in GATE, and this is also giving you huge weightage in your ES prelims also. Okay, so this is how you go about it, this is how you solve the problems, and this is how you move forward in this statically indeterminate problems. Just go by the basics and you can easily solve the problems. Okay, then one more case comes out as when your support is yielding by delta naught. For example, the support yields by delta naught. So what will you write down? You will write down the whole equation, and then you will not equate it to 0, you will equate it to what? Delta naught. Because net deformation in the system is delta naught, isn't it? And always write down, in this case, you write down the system as tensile, because this is moving forward. The support is not compressing, the support only yields or moves ahead, and that can only move when you have tensile system. Now, in this question, we got our RA as minus 3P by 2. So what is the negative value implies that the RA direction which we had taken is wrong. Only the magnitude is correct. The direction should be what? Opposite to it. Because what are we getting? We are getting minus 3P by 2. Actual value of the magnitude is 3P by 2. But the minus sign here is indicating the direction which I had taken initially was wrong. And why it wouldn't be? Absolutely. I can take whatever direction I want to. But at the end, again I will get the correct one because of the equilibrium equations. And that's how I solve these kind of problems. So